Hello, everybody, and welcome to the Bureau of Economic Geology Summer Seminar Series. Can everybody hear me?
Yep.
Okay. Well, I'm Evan Civil. I'll be your host today. Today is the last seminar of our 2020 series. So on behalf of Jana Robinson, Aaron Everett, and myself, I do want to thank all the people who presented this summer. The talks were fantastic and we learned quite a bit. I want to thank you all, the audience, for tuning in every week. These seminars were a great way for us to stay connected while we continue to work remotely and in our new environments. If you're interested in presenting next summer, feel free to email me. I'd like to hear from you. So today, our speaker is Dr. Ken Wisian. Ken is an associate director for the Bureau and is responsible for coordinating environmental research. He came to the Bureau from the Center for Space Research. Previously, Dr. Wisian was a senior state executive responsible for disaster recovery, oil spill prevention, and coastal infrastructure and environmental protection for Texas. As a military officer, General Wisian participated or led military disaster response efforts for the Space Shuttle Columbia crash and multiple hurricanes. Ken is a geophysicist whose main research is in geothermal systems, modeling, and instrumentation and data analysis. Other current research includes autonomy in drones, applied gravity, planetary geology and space exploration, infrastructure resiliency, and international relations. I ask that as we begin, you silence your microphone as a respect to the speaker. And if you have any questions, please ask them in the chat and Ken will answer them at his first availability. With that said, I'll turn this over to you, Ken.
Welcome. Okay, thanks, Evan. Well, welcome everybody. For this last summer session, we're gonna go far out, man, and talk about search for extraterrestrial intelligence. It's a wide-ranging subject, and we're going to cover a lot of ground, so hang on. I won't go too deep, but happy to drill down on the topics that really attract your interest. I'm guessing that in a group like this, there's a fair number of you who already know a decent amount about SETI, so we'll see where that goes. My opening slide here is one, just to show you that I collect titles for some obscure reason, but I bring a lot of legacy connections with me in this topic from before I entered the Bureau, in case you're wondering why someone who does environmental geology has all these space things. But I'm still associated with the Center for Space Research and have some simmering work going on there. A lecturer in aerospace engineering, and in connection with that, I'm actually teaching a course that just started yesterday, an in-person course on the search for extraterrestrial intelligence. So I'm actually teaching this subject as an undergraduate signature course right now. Also a founding member of one of the newest research centers here at UT, the Center for Planetary Systems Habitability, which is a joint venture of natural sciences, Cockrell Engineering, and the Jackson School. So quite a interdisciplinary work there. And I'm also a fellow on the British Interplanetary Society, which is the oldest space exploration society in the world. So that's kind of the basis I come to this from. And towards the end of this, we'll also get into my most recent academic papers, which are in this area too. Again, kind of a legacy of my work before joining the BEG. So with that, I'll get on, and to reinforce what Evan said, please chime in with questions at any point, especially if I use a term or something that's not known, or just to go a little deeper on any of these. And you can chime in verbally or in the chat room. I'll try to keep one eye on the chat room too. So with that, we'll get into it. First, find the right button to click here. There we go. First, I need to set the stage a little bit. And again, with this audience, probably not too deeply, but this is a nearby galaxy that's a lot like our own Milky Way. It's a spiral galaxy, a middle range spiral galaxy of probably around 200 billion stars or suns, just like our own Milky Way. And in our galaxy, we'd be in a relative position shown here. That means our sun and the solar system, although they would not be visible. Way too small and insignificant to show up on a galaxy-wide photo like this, bear in mind that almost, not quite everything, but almost everything you can see in the night sky, if you go out into the countryside, is from our galaxy, from the Milky Way. And specifically, when you're looking out in the night sky, you're seeing mostly stars that are from a pretty close region to where we are in the galaxy. Yes, if you look towards Sagittarius, you can see a glow, a general glow from the center of the galaxy, but bear in mind that we are in this. So when you're looking at the Milky Way, you're essentially, instead of looking at a galaxy like this from about 30 degrees down angle, you're looking at it from about 0 degrees, right along the thick, flat plate of the galaxy. So that's where we stand in relation to our galaxy. Now, let's take a look at this shot. This is one of the more famous photos in astronomy. It's a part of what's called the Hubble Deep Field. So the Hubble Space Telescope back in the 90s tried something really new. And that is, it looked at a blank part of the sky, something that had nothing recorded in it. And it exposed the sensors for almost 400 hours. That's a lot of time on the Hubble telescope. This is the result. The diameter of this field you're looking at is about equal to a tennis ball 2 football fields away from you. That's how much of the sky this is looking at. And what you're seeing here are thousands of galaxies, on average the same size as our Milky Way. The only thing in this photo that is from within our Milky Way is this one star here, some lone star that happens to be, you know, out in the boonies of our galaxy. Every other speck of light you see in this photo is an entirely additional galaxy. And this is just a view that's about a pinpoint at arm's length from your eyeball. What this and other similar photos that have been taken in the past few decades show is that there are probably roughly 1 trillion galaxies in the visible universe, in the known universe. So you multiply that trillion times, on average, let's round down and say 100 billion suns per galaxy. You've got a lot of stars and planets, and I'll get a little bit more into that in a minute. But that in turn really begs a question. If there are so many trillions of opportunities for life and intelligent life to arise in the universe, why haven't we found any yet? That is the Fermi Paradox, one of the most famous questions really in modern science, particularly in astronomy and exobiology. Originated by Enrico Fermi, well-known atomic and nuclear physicist, over lunch with colleagues back in the 1950s, where he just asked us, well, where is everybody? This paradox is now a major field of research, combining many disparate disciplines. So, where are these critters? And particularly a follow-up question, are they this type of alien if we ever find them? By the way, if you're looking for a fun movie this weekend, Mars Attacks. It's a blast, and it's a real send-up of 1950s B-grade science fiction movies. So you have the Fermi Paradox. Where are all the aliens? Underlying that is something called the Drake equation. Originated by Frank Drake in 1960. He's the father of radio-based search for extraterrestrials. And this is a very simple string of coefficients that is designed to get you to the number of civilizations in our galaxy, not in the universe, just in our galaxy, with which we could possibly communicate. And it uses a few terms here: average rate of star formation, fraction of those stars with planets, fraction of those planets that could develop an ecosystem, fraction of those that could develop life, develop intelligent life, develop interstellar communication, or frequently as termed, develop a technological civilization, and the average lifespan of those civilizations. We've known R for quite a long time. It's on the order of 1 star per year. We now know, thanks to the past couple of decades of exoplanet hunting, where we found thousands of planets around other stars, that the fraction of those of stars with planets is basically 1. Some stars don't appear to have any. Most stars appear to have multiple planets. And we can also state that somewhere around 1 in 10 or 1 in 5 falls in what's called the Goldilocks, or the habitable zone around stars. The rest of these coefficients are pretty well completely unconstrained. That's why this doesn't really work too well as a scientific equation. It works better as something to structure your thinking, structure the direction of research and exploration, and understand the factors involved. Depending on who manipulates these numbers, you come up with anything from we're probably the only civilization in the universe to there may be 10,000 other civilizations in our galaxy. So it has quite a range, and frankly, in some ways, that's one of the fun areas of fun things about this area of science is you can speculate and no one can actually prove you wrong. I'm only going to drill into a little bit of that equation. It's all fascinating, and you can go into a deep dive on all those different terms. But one I want to work on a little bit here, which I think is one of the more significant ones, is the intelligence part. You know, what's the likelihood of intelligence arising? And then by way of backing up a little bit, you know, we don't have great case examples. We've basically got one planet where we know life arose, but it sure seems to have arisen pretty quickly after the Earth formed, in geologic terms anyway, on the order of 500 million years or less. It did take a very long time for intelligent life to arise, and we've used up most of the 4.5 billion years that Earth has existed. Getting to the point where we are now, we're only in about the last 100 years has our technology really taken off, and less than that we've really been capable of interstellar communication.
Ken,
Yes.
I've got a question about that. How do you define intelligent life? I mean, do we think
that's a whole sub-branch of this question.
Okay, all right.
You could, well, intelligence, I can't think of a better analogy. It's like the Supreme Court ruling on pornography. You know it when you see it. Intelligence is kind of that way. But what I think is a little easier to define is you can be intelligent without being technological. And I'll kind of circle back to that in just a second. Actually, about one more slide. One thing that I think is significant is that I think the indicators are growing as our knowledge gets better, that intelligence is a direction that evolution tends to drive in. Now, maybe not all that frequently. You know, there's, I don't know how many millions or billions of different species of life here on Earth, and relatively few have any level of what we call intelligence, but there are some interesting factors within that. A little more broadly, convergent evolution, I think, also drives home this point on intelligence. It's a fascinating part of evolution to look at, and that is how evolutionary pressures, environmental pressure, whatever you want to determine it or call it, tends to drive very different species or approaches that end up at the same point evolutionarily. Several examples of that. Sharks, dolphins, many other types of sea creatures independently, and remember sharks and dolphin, you know, fish versus mammal, independently arrived at almost the exact same body shape because it's efficient. It's an efficient way to move quickly through the water. Eyesight in nature is particularly interesting. We can now say that at least 8 times nature evolved eyesight independently. That's a very powerful argument for convergent evolution. And there's many variations on eyes in nature, but eyesight has developed independently at least 8 times that we know of so far. And intelligence similarly has arisen independently multiple times. this goes back to that question now. How do you measure intelligence? There isn't one agreed upon way, and it gets very complex. There's very many different aspects to intelligence. But as a first order indicator, brain body mass ratio, or just by flipping the numbers, encephalization quotients, are a pretty good first cut at it. And when you look at that, and in this graph, this is brain mass versus body mass for a wide range of species, with one being essentially an average, a slope of 1 here. And what you see is that as far as distance from that one line that would be here, we're as far away from it as any species on Earth. And that equates to an encephalization quotient of 7 for humans on average, or a little higher. The next highest is dolphins at 4 to 5. So a moderate difference from us. Chimpanzees are down around 2.5, so a little farther away. In general, you can see that warm-blooded animals do a lot better than cold-blooded animals as far as encephalization quotient. Now, admittedly, this is a crude measure. It doesn't take into account a lot of things, types of intelligence and such, but it's a good first-order indicator. Human ancestors, you can see, also have a steady evolutionary path away from the line, or in other words, towards greater intelligence. So one thing you can see here is multiple very independent paths towards relatively high intelligence. And you could throw in here some interesting other species. There's a lot of work done on crows as being intelligent. Unfortunately, octopi aren't on here, but they're another very interesting example that has involved not only a different eye, but also a very different brain structure, where they have a very distributed brain, including subbrains in each of their limbs, just for manipulating their limbs. So you have an interesting deal. A lot of this, I think, and let me see my next slide, yeah. Plus evolutionary history showing that over time, within species, or at least groups of species, you have some clear trends towards increasing brain body mass ratios. And so taking all that together, it tells me that yes, there is an evolutionary drive or pressure that makes it worthwhile to support a relatively energy intensive large brain as an evolutionary advantage. And this is another one of those entirely independent or energetic subfields in this area. So I don't know if that's completely answered your question. Well, let me back up one more. So we've got dolphins, which appear to be probably the next most intelligent, but they don't have a technological civilization. They definitely have culture. They seem to have the full range of emotions. They have humor, curiosity like us, but no tool use that has allowed them to develop a technological culture. So, well, actually, I don't know if I can say no tool use. I think they have some minimal use of stones in some ways. But what are they missing? They're missing a really good way to manipulate the external environment like we do. So hands make a massive difference in developing a technological civilization or something along those lines. The rejoinder there would be, okay, so what about the octopi? Why haven't they developed technological civilization? And I would say there, it's probably, my guess would be it has to do with that distributed brain. I'm not sure they have quite as much central activity. A lot of their brain is devoted towards those very complex tentacles they have to control. Comparatively, our limbs are a lot simpler. Okay, let's move into the search for extraterrestrial intelligence, known as SETI again. And it revolves around a few different main things. You're looking for signs of aliens somewhere in the universe. It's a little bit distinct from just looking for signs of life. SETI is looking for signs of a technological culture, one that would be capable of communicating with us over interstellar distances. And that comes down to a few main categories of things you're looking for. One is leakage. So the equivalent of our stray radio or television signals have been broadcasting out into space for, about 100 years now. There's also looking for deliberate long distance communications. So radio signals or such from someone else within their own society or outbound, deliberately beamed to outside civilizations. And then the newest area of research is looking for techno and biosignatures. So that's looking for not signals, not communication signals anyway, but other evidence that there's life or civilizations out there. How do you do that? Well, our technology is almost to the point where we could detect or take the spectrograph of an alien planet atmosphere. If we could do that, that's a big step in this direction, because if you can measure what's in an atmosphere, you can sense some things like disequilibrium chemistry, which results in things like our oxygen atmosphere, which would be a strong indicator of life. You could sense directly pollutants or other things that are a result of technology, which would be a clear indicator of a technological civilization. You could also detect, if they're doing engineering on an interplanetary scale. One thing that's probably impossible to hide is the waste heat. And so there have been active surveys to look for extraneous amounts of infrared energy coming from star systems. None found yet, by the way. That couldn't be explained other ways. By the way, this photo is the Arecibo radio telescope, until recently the largest single dish telescope in the world. Unfortunately, just a couple of weeks ago, severely damaged when one of the support cables broke and tore out a big chunk of the telescope. But I'll come back to that in a minute. And on the right is an example of what was a deliberately beamed outward bound signal from Earth to stars quite a ways away, giving a simple basic message to aliens that we're here. Now with radio telescopes, two main things: targeted search or whole sky scans. And there have been both conducted in the past and ongoing now. Based on what we understand about planetary evolution, the ability of life to arise and such, there have been targeted listenings, for lack of a better word, for good candidate stars in the region. Those are ongoing. And then there are also regular all-sky surveys, where you just sweep the whole sky, not knowing necessarily where to look, but just hoping you'll detect something. A lot of these started out as, spare time projects on radio telescopes, evolved into substantial government funding in the 90s and such, and now it's back to more private mega donor funded projects, including the most active works that are going on funded by I'm drawing a blank on the name again all of a sudden, but one of the tech billionaires, not Bezos or one of the best known ones, but Sergey Brin, I believe, has funded several things along these lines. Key factors, oh, by the way, the bottom photo, Owens Valley Radio Observatory, which has a major role in this field, visited that place a couple of years ago. Fascinating to see all those radio telescopes out in the desert, just on the California side of the Nevada border. Factors that go into this: how faint is the signal? This goes, and how big is your receiver? This goes back to the question of our radio broadcast. How far away can they be picked up? And that's the radio engineers really have quite a debate going on that. Theoretically, there's no limit. Well, actually, there's not much of a limit on how far away you can detect TV signals from Earth, but there are some very practical limits, including being able to pick it out in the noise, because beyond a few light years, our radio and TV signals are really extremely faint. The most likely candidates for traveling a long distance beside our directly beamed or intentionally beamed signals are the interplanetary radars, looking at asteroids and such. Oh, and this is also one of those areas that was one of the original citizen science avenues. And until a few months ago was going quite well. It's gone into hibernation for the time being, but SETI at home was one of those original projects that allowed you to turn over your computer's spare CPU cycles to a project that then fed you chunks of radio observatory time signal to look for signs of an artificial signal. And that ran for decades. I used to have one of my computers running that. I'm sure something along those lines is going to come back pretty soon. I'm not seeing any questions in the chat yet, but please ask if you have any. More recent development, as our technologies increase, we've realized that lasers are really probably a more efficient way to communicate over interstellar distances. So again, a fairly new area. There are pluses and minuses to using lasers between stars. Not quite as long range as radio, but particularly if you use infrared, you can get a fairly decent way through the galaxy with a laser signal. You can definitely get a higher information content into it, and you can better focus it compared to a radio signal. So that's ongoing, and there are multiple projects that regularly scan the sky for any signals along those lines. Again, no verifiable candidates found yet. And then,
can you have a question in the chat from Ramon?
Oh, here we go. Okay, does the Drake equation take into account space-time? Implicitly, yes. It's kind of a wash in there because it's factored into what can you communicate in real time. So the life of the civilization kind of factors into that. If you're 1,000 light years away and the life of your civilization is 500 years, then the best you're ever going to do is a one-way, one-time signal. And it's a major factor because, you know, if we're talking about actually carrying on a civilization to civilization contact, the lag times are incredible. I mean, the nearest star to us is 4.2 light years away. That means a round trip signal time is 8.4 years. You think our lag time is bad when we're doing these video conferences when you have 1.5 seconds. Try, you know, when you're talking decades or centuries long lag time between send and response. Now, yes, you can be broadcasting just information one way. In the meantime, you could broadcast Encyclopedia Galactica or something. But it is a major factor in this. The time it takes the fastest thing in the universe, which is light or electromagnetic waves, to travel, is a real major limit on this. And in fact, you know, go back to this picture of this galaxy. On this scale, if this were the Milky Way, which is about 100,000 light years across, our 100-year light bubble would be about like this. So even if there are 100 civilizations scattered around the Milky Way, the odds are our light bubble or our radio bubble has not reached anyone yet to even be aware that we're here. Okay, techno-signatures. Again, waste heat. Oh, something I didn't mention earlier. If you got the ability to travel between stars or at least deep space, then Starship drives probably generate a detectable signal, spectrographic signal over interstellar distances, whether it's an engine that's in a spaceship or what we're on the verge of having the technology to do, which is launching laser or microwave driven solar, well, not technically solar sails, but think of them that way, big space sails. The biosphere changes I've mentioned. We're a little farther away. The new space telescopes that are about to go up will just barely probably be able to take a crude spectrograph of an atmosphere. The next generation beyond that would probably have enough sensitivity to be able to detect artificial light, for instance, on the night side of a relatively nearby planet. So you're talking within probably far less than 100 light years, but that's still thousands of suns. So there's various ways besides an actual intentionally sent signal that we might be able to detect extraterrestrial civilizations. And as you can see, NASA's involved with this. All the major universities have programs in some way or another like that, including to some degree UT. Our strengths are more in finding the planets, characterizing their environments and such, but we also have some work in these areas. Okay, so say we get a message. What are we going to do with it? Well, you know, here's where we get into another set of problems. There are still languages here on Earth that we can't decipher, that were written by humans. So the same species evolved on the same planet, the same brain, and we still can't decode some of them. We wouldn't have been able to decode a lot of ancient tongues if it weren't for things like the Rosetta Stone or their equivalent. We still can't speak Dolphin, and they clearly have a language. So there's some real problems here. A lot of scientists, and particularly physicists, will say, well, we can use math as our basis for communication. And yes, I'm quite confident that we could probably understand each other's math fairly well, but no one's shown me a convincing path from understanding math to conveying philosophy, emotion, meaning based on a math-based language. And this is even acknowledging what computer languages are, but that's not a completely valid argument that way. So, you know, that's a whole interesting problem in itself. I will say that just the detection of a confirmed signal would be obviously revolutionary. In fact, that leads us to the question of what would be an impact. And I see something else coming in here. What information do you handle about expected or explainable evolutionary trend of the human brain and the apparent inexplicable leap that occurred? Well, that's a good question. And actually, go back to that encephalization quotient diagram. There's actually a pretty smooth continuum in the evolution of brains. And that's quite an interesting area of research right now. And I think that's an area that artificial intelligence has quite a dialogue going back and forth with neuroscience, showing us and showing each other's fields some of the ways that these things develop. We've learned an awful lot by seeing how machine learning works, and vice versa, figuring out how the neurons in our brain work. And like I say, it's a pretty smooth path from, you know, pretty low level animal intelligence up to our level. Now there's two very different subgroups within that. There's task specific, and I forget the technical term for it, intelligence, and then there's general intelligence. You know, path specific or task specific is like predators evolving a better ability to spot prey, you know, that kind of thing that has a very unique feature. It's not a kind of a general purpose adaptation. One of the key things is our brain and most of those other higher encephalization quotient animals seem to have gone down the path where they started developing general purpose intelligence, which allows a lot more flexibility, ability to adapt to changing environments, which is pretty clearly key to our evolutionary success. Although even that barely saved us from quite a genetic bottleneck. So an interesting area. You know, having worked also at least briefly in an artificial intelligence startup, it's fascinating to see where that's going nowadays. And frankly, pretty much all our machine learning is task specific. It's not artificial general intelligence. That's still the golden ring that AI scientists are driving for, but which there isn't an obvious near-term solution to. So back to what would be the impact of a validated message. And this starts to get into my recent publications on the topic. I don't know how many of y'all are familiar with the cartoon XKCD, one of the best nerd cartoons around for programmers, physicists, and other related scientists. But I'll give you a second to digest this. Hopefully this is readable. Okay, a little bit of backtrack. That's the whole SETI thing started in 1960, where Frank Drake, the guy I mentioned earlier, beamed out a signal, or actually no, did a listening project. And it's gone on in different levels of activity till now. Okay, the impact of the discovery. I think everyone pretty well agrees that in the long run, it would be huge. You know, it definitely would be one of the all-time great changes in science, even in the understanding of ourselves. But I think there's very good evidence that it would be practically negligible impact on the day-to-day lives of most people. You know, if you're more concerned about keeping your job, putting food on the table, yes, it would be a mildly interesting thing to know that, yeah, we finally discovered alien life, but would it change your life? No, not in the near term. And I think that can be backed up with some very solid case studies. Back in the early 20th century, when actually a large percentage of people believed that there were aliens on Mars. Did that change the course of world events? No. There's been a couple of other false alarms through history. If you go back thousands of years, even ancient Greeks thought that other planets probably had life on them. In the 1600s, a lot of scientists assumed the moon had life on it. So probably not much impact on most people day to day. Yes, a few people whose worldview might not be compatible with other intelligent species might get upset, but that's been widely considered to be a pretty small problem. So, you know, the existential risk of discovering a signal from another species has been thought to be pretty small. In fact, just non-existent, really. Why? Well, mainly because the chances of aliens who find us tasty arriving on our doorstep is considered to be pretty low. The physics of traveling between the stars is pretty daunting. There's just so much difficulty to it, and there's so much other resources available in the universe that it seems, in my mind, pretty unlikely that anyone needs to take over planets or would find us tasty if we're even biochemically compatible or could be eaten. So it's been assumed that there's negligible risk. But I think that that overlooks a major factor. There was this is just a recent New York Times article I found, which I like the headline of. Side tangent here, this radio telescope in the background is the newest record holder for single dish antenna in the world. It came online, I want to say it started its test runs a couple of years ago. It's based in China. And it has, as part of its government-directed mission, conducting SETI. So it's part of the Chinese government's official policy. Beyond SETI, there's been an active debate about METI, messaging extraterrestrial intelligence, and that's the beaming out of deliberate signals. And that's quite a heated debate within this field. The legalities of it are pretty much non-existent. There is some international law in space. It is very weak. And there are also scientific agreements, but they're non-binding or not even universally adopted to share information if a signal is detected or before sending something out. A lot of people argue that, well, the barn door is already open. You know, we've been beaming out into space for a long time, but again, I argue that technologically, that's not that easy to pick up. So it comes down to a question of, is it wise to shout hello into the wilderness? Human history is not a good case study of this, where civilization encounters generally have not gone too well for the civilization that's on the technological low end. And bear in mind, we are about at the level of a zygote as far as interstellar civilization goes. We have only in the last 100 years achieved radio communication. So the odds are anyone that we found would be millennia to even billions of years more advanced than us. Would they be ET, or would they be the alien from Alien movies? We don't know. But nature seems to be universally a life form, eat life form universe. So my thinking is fail to the safe side. You know, if in doubt, play it safe for now. And I think it's rather arrogant that some scientists take it upon themselves to broadcast on behalf of humanity out into the universe saying basically, here I am, not knowing what's out there and generally making a pretty naive assumption that advanced civilizations are completely peaceful. That's a whole nother subtopic I could go into. I'm going to skip over the law and space, but it's pretty thin on this area. In fact, it's so thin that you don't really even need to be a lawyer to read it. It's just a few pages of international treaty that are actually fairly understandable. Okay, so there's SETI, assumed to be safe. There's METI, which has a very active controversy and fight going on in science circles. But I think people missed an important point here, and that is the threat we present to ourselves. So the background on that is that there's two main schools of international thought. There's the realist and the idealist school. Idealists believe in principles, you know, good intentions and such being the dominant factor, you know, win-wins for everybody, that kind of thing. Realists tend to take the view that no, might makes right. It's this kind of a survival of the fittest kind of environment. And that traces all the way back to one of my favorite authors, Thucydides, who wrote the first really comprehensive political military history on the Peloponnesian War back in the 5th century BCE, where he says, well, he quotes the Athenians as stating, the strong do what they can and the weak suffer what they must. Now, I don't think international politics is played strictly on this game. It's a blend of idealists and realists, but a lot of governments do believe that this is what matters. Also, Thucydides said that the dominant cause of war is fear of the other side gaining dominance over you. And I still think that holds true. So again, my favorite book here, which I'd love to teach a course on, gives you a 2,500-year perspective on how human nature, politics, and warfare has not changed over the length of recorded history. So that brings me to my point. My main thesis is that controlling communication with an ETI could be the biggest prize ever in international competition. Why? It goes back to that technological lead time that anyone we found would probably have on us. You know, civilizations that are hundreds of billions of years ahead of us, their toys and vacuum cleaners could be tremendously beyond anything we know. There's a great Star Trek episode where someone accidentally leaves behind, I think, a communicator, and that comes back to haunt them later on, or leaves a book behind. Well, that kind of thinking is what drives my argument. So even just listening to ETI could have huge technological benefits. Why would that be a problem? Well, because a nation state that perceives the potential for technological dominance in world affairs will go to great lengths to achieve that dominance. And if communication with ETI requires a fairly substantial infrastructure of specialized equipment and specialized people, say on the order of a major radio observatory, then that is very subject to physical control. Much like resources like nuclear power plants or other facilities have well proven in the past 50 years or so to be subject to. So if a superpower thinks that they can gain dominance over world affairs by monopolizing that communication channel with ET, then game's on, so to speak. A couple other assumptions in here. Well, yeah, you need the specialized scientist, and that there's no ETI lurking within our solar system that could fact check what we tell them if there's a two-way communication channel. But even one way could be sufficient. If there's technological knowledge embedded in the signal we receive, then that could make all the difference. And here's another key thing. A lot of people argue, well, I've had it argued, not a lot of people, because it's a brand new paper, that, well, no, there really isn't any technological advantage to be had because you can't control it. Things leak out. I mean, look at the nuclear bombs. We couldn't keep that secret. That was the most valuable thing in the world. But that doesn't matter. What matters is perception by the leadership. If the perception they have is that they can gain dominance, then that's what they will act on, not on what might be proven to be in the long run not a viable path. It's on perception. And we've seen that so many times when people think there's good cause or they can win a war quickly, which almost never happens. So it's the perception that matters, not the reality, unfortunately. And this opens up a whole range of actions from simple diplomatic things all the way up through and including nuclear warfare. Cyber and espionage would be common things. You know, part of this is you want to preserve your abilities while denying the enemy theirs. You preserve yours by protecting it in every way possible. You deny theirs. You can deny it by blowing it up, but you can also deny it through cyber espionage, through taking out their specialized people that have the knowledge they need to operate that kind of thing. There's a lot of ways that things like this can go on. And in connection with that, I've suggested that scientific bodies that do this work probably need to rethink their physical security. And I know I had a big dose of that when I commanded a Predator unit in the war, which is a new thing which really we had to invent security for. When you're conducting combat from the homeland, but you're a significant terrorist target, you have to change your game quite a bit in physical security and the security of your personnel. So we're about at the end of what I wanted to cover. I can go into a lot more of this in detail. A few things first before I finish and ask for more questions. There is hope here. I mean, it's not all gloom and doom. One, this is just a possible scenario. I don't necessarily state that it's the most likely, but I think it's viable enough that we need to be aware of it and governments need to take action. The scientific community can do a lot to foster this. One of the best ways I think you could keep the superpowers from trying to monopolize is to make sure that the information got out quickly, such that a government couldn't lock it down. You know, can you have some sort of instantaneous sharing of data as soon as it comes in without interference? Yeah, we could probably do it. Authoritarian governments might be a lot harder to do. And our own technology is continuing to advance where we can solve problems ourselves, hopefully make the communication decentralized enough or easy enough to where you don't have to have that major infrastructure or specialized skill sets. This was my one of my two recent papers done with John Traphagen. He's an anthropologist in the liberal arts religious studies department, published in Space Policy last month. And we have another one that came out in the Journal of British Interplanetary Society a couple of months ago too. So that concludes it. We have a little time for questions. How about some more? I threw out a lot of wild stuff there. And here we go. Practically, how would someone monopolize one-way communication with ETI? Well, the key is what level of infrastructure does it take to receive the signal? You know, if it's broadcasting from within our solar system at a fairly high power, then yeah, you could probably pick it up with a backyard antenna. But if it's something coming from 100 or 1,000 light years away, even something that started out as a megawatt power signal, you're talking microwatts by the time it gets here. Currently, these kind of signals to pick up even from, well, to pick up from a civilization equivalent to ours technologically, they can beam out a pretty powerful signal. to detect it at more than a few light years away takes resources on the scale of what you see here. So when you talk about facilities like this being required, there's a dozen of these capable in the world. That's a small enough number to where, yes, any of the superpowers could try to physically control those or destroy them. So that's how you can communicate even a one-way channel for listening. Good question. More.
You have another question above that. A few questions, actually.
Oh, I see. Some of them scrolled by me before I could see it. So let me back up here. Okay. What information do you, oh no, I did that one. Are Voyager 1 and 2 now in interstellar space, sending signals to places besides the Earth? Okay, one, they are, well, they're kind of in interstellar space. They're outside the sun's heliopause. So they're outside the sun's wind influence, I guess you'd say. They're still not as far out as what's called the Oort cloud, which is kind of the final body of our solar system. It's the long-term reservoir for comets, which is probably out there at close to a light year. The Voyagers and the Pioneers, which are farthest out probes, let's see if I'm remembering, I was just looking at this the other day, they're about a light day out right now. So they're just creeping out, and they're the fastest things we've ever launched. And by the way, they won't pass closer than a few light years to another star for at least the next 50,000 years. So they're not going to end up in anybody's backyard anytime soon. They are barely broadcasting signals back to us still. So, you know, that beam is wider than the Earth, so some of it is going past us, but it's barely detectable with our biggest scopes, and they're only a light day away from us. So would that be detectable over, you know, the minimum of 5 to 10 light years to the nearest star in the direction behind us that they'd be going? No. They are carrying information with them. They're carrying plaques and records that were designed to tell aliens about Earth, but that was meant for domestic consumption, not really as a serious message to aliens. Is there a theory that says probability of ET life is large, but their civilization lifespan could be relatively short? Yeah. That is, no civilization around long enough to develop interstellar effective communication. Yeah, that's a distinct possibility. We don't have a clue as to what the average lifespan of a civilization is, especially an interstellar capable one. That gets into a whole nother discussion on what are called great filters. What are those civilization ending things that we may or may not be aware of? You know, there's obvious things like a meteor big enough to take out the dinosaurs could take us out. We could destroy our own civilization. We could cook ourselves out of existence with climate change. There's those kinds of things we know about, but we don't know about other things, or we only have an inkling. Unfortunately, the technology is almost down to the single person hobbyist to engineer a virus that could possibly pose an existential threat to humanity. So all those things could cut our civilization time short. There is a common misunderstanding of what's meant here. A lot of people point to Earth's history and go, well, civilizations last on average a few hundred years. That's specific, I would call that specific cultures aspect of civilization. So like Rome rose and fell, you know, the British Empire had its heyday. Many other civilizations in that sense of the term have risen and fallen. But human civilization as a whole has been on an inexorable march towards higher technology for thousands of years now. So I look at us as one continual civilization. How long we last going forward is completely unbounded. And so it's an interesting question, it's a fascinating question, but there's an open single data point on that. Which technology advancement do you think would make a huge difference to communicating with intelligent life and other systems? Within the known laws of physics, it's really just evolutionary advancements on our ability to do radio and laser communications, because that's really the only viable way to communicate deliberately. Our telescope technology increasing can allow us to detect unintentional signals a lot better, but really it's radio, and radio to include microwave, and lasers to include IR. Other things, the laws of physics really kind of preclude them. If we were to have something way outside known physics like tachyons that travel faster than light or something like that, then that would be a revolutionary change. But right now, as far as anyone has any indication, Einstein's quite a speed cop, and the speed of light is our limit to communicating with anybody. Other than that, it's just building bigger and bigger antennas and beaming more and more power in various forms. Let's see here. I love having all these questions come in. Thanks. And by the way, if we run out of time, I'll keep talking till my voice gives out if people want to stick around, or unless we're booted by the organizers. Practically, I did that one, sorry. Oh, yeah, thanks to Evan and Jana. Yes, thank you very much for organizing this. Thanks for letting me kind of do this wild topic. This has been fun. I've enjoyed the other ones. I know last week's on Coop. It turns out Coop is my favorite radio station, so I love that talk last week. From Emily, this is a great topic, interesting. Thanks to everyone. Yep. What message would you send out that you think would garner a safe response? Well, that's the question. See, I don't know that there's, I think just even waving hello poses an unknown level of risk. And when you can't even quantify the risk, I think it's wiser just to be quiet and listen till we can figure out a lot more. So I favor keeping our mouths shut for the time being. And by the way, as time goes on, we radiate a lot less into space. So there's a brief moment in time where we're really leaking radio. But you know, as we've gone more and more to landlines, to optical cables and such, the level of noise we're putting out is a lot lower. Thucydides would definitely come down on the side of don't broadcast, at least not yet. I mean, there's no world agreement. There's not even a hint of UN. A proposed agreement was presented to the UN by one of the international science bodies decades ago, saying, here's a draft protocol for how the world should handle this whole topic. And they said, thank you very much, and filed it. And that's where that stopped on an international basis. Of the planetary systems we've identified so far, which do you feel are the best candidates to focus on? That's a pretty straightforward answer. You can go to websites that list what systems that we found have roughly Earth-sized planets inside what's called the habitable zone. And there's a dozen to 24 of those that we know of so far. We really can't characterize which of them even have atmospheres yet, but they're our best candidates going forward. And so, yeah, you can look at those. They're generally in the range of relatively nearby, a few tens of light years. Well, actually, no, some are only a few light years away, out to maybe 1,000 light years away. So you could look at that. Now, what that doesn't account for, and what we haven't figured out a way to account for, are potentially habitable moons that are deeper out in solar systems. So for instance, the icy moons of Jupiter and Saturn and Neptune have the real potential for life, although because it's inside the ice shell of the planet, maybe not a technological or communicative species. But the hottest area for looking for life in our solar system right now is the icy moons of the outer solar system. And there are people here at UT, part of that Center for Planetary Systems Habitability, that are lead scientists on some of those probes that are either in process or going to launch in the near future. Okay, thanks back out from Evan. Before closing this seminar, Mark would like to say a few words. So I don't see any more questions coming in. I'll shut up and give the floor over to Mark.
Yeah, hey, well, Ken, that was a lot of fun and absolutely fascinating. So I just recently read a science fiction book, The Three Body Problem, so that struck home. Anyway, I just wanted to say thank you in a very big way to Jana, to Evan, and Aaron. for organizing the summer seminar. You guys, got onto this very quickly, and I think you put together a wonderful program. I mean, I just was looking at the list. So we had energy poverty, we had the perfect ice cube, we had the moon, we had stress management, air battles, record collecting, Carlsbad Caverns, people, and today, looking for ET. So it's just a real broad and diverse collection, and very enjoyable. And so I know that it takes some work on your part, so I just wanted to thank you all for putting this together, and very well done, and I think everybody has enjoyed it. So
Thank you very much.
Much appreciated, folks.
We appreciate that.
Thanks, Mark. Thanks, Mark.
And just to put it out there, a lot of these videos will be on YouTube. The Bureau has its own YouTube channel. If y'all haven't checked that out, y'all definitely should, and we will probably send that link out. So if anybody missed one, go ahead and view it on YouTube.
Thank you.
Well, have a great weekend, everybody.
For joining us this summer.
Thank you.
Thank you.
All right. Well, everybody have a good weekend, and look forward to the next year with you guys.